Morning to everyone. I was trying to ask Ernie if he heard whether my mic was on. Is my mic on? Thank you. Now, what were we listening to? It was Neil Diamond, and what was your choice? Forever in Blue Jeans. Okay. And you look like an Eskimo back there. Hat, coat. It's really not that cold in here. Okay. In terms of what we've been doing, you were doing some multiplications with polynomials. How did that go?
Great. I love that.
Okay, a couple problems with difficulty, but overall? Okay, so this is good. Now, what problems were we having trouble? Isaac?
Okay, 4y.
So I need to write something is what you're telling me. Okay. And watch, and so I can read your symbols. So 4y, and then what? That's what you're wanting?
Yeah, parentheses.
So it's up there, and then parentheses. Is that
Put another.
like that?
Yeah, but no. In it.
Is this what you wanted?
Then put a 5 outside. On top of 5 next to it.
An exponent.
Yes, that's what's up.
Isaac, you and I need to have a conversation about speaking mathematics. Open parentheses, 4y to the third, close parentheses, exponent 5.
Sounds like a plan.
That's what I thought. Now, what's missing there that you would want to write in? Isaac, what's missing that I want to write in? It's your problem.
Is this fine? Is this safe?
I know. What's missing that you want to write in?
I don't know. That's why I'm asking for help.
No seeing.
On what?
An exponent that's missing. That's the key. I just wrote it. The 1.
For 4?
Yes,
I thought 4 is his own number. I thought
it is. It's also 4 to the first. It's the missing 1. That's why I asked the question, because once you do that, this is 4 to the 5th, y to the 15th. Done. Yes. Unless you were asked to multiply 4 times 4 times 4 times 4.
Yes, that thing.
That's 256. But you knew that from the counting unit.
I finally got the answer correctly because I used the help thing.
I know, but the point being that we've said yesterday, the missing exponent is the key to many of these problems. And I did that yesterday in quite a few of the problems. If you have a 4, it's understood to be 4 to the first. And then I'm using this particular property, not a property so much as a rule that you're using, which says that this is going to be what? A to the mn. End of question? Okay, before I get to James, Efren, you had a question. Which one? You said the last two. Can you give me an idea which one?
Yeah, they're right here. 5y to the second.
Okay, so I'm going to read just what you said. Is that what you meant?
Yeah, parentheses.
Open or closed?
Yeah,
Open parentheses.
3y
3y
plus 4.
plus 4
Close parentheses. Open parentheses. Y.
close parentheses. Okay. Now, what did I suggest yesterday for this problem? Take care of these two binomials first with FOIL. So that was going to be 3y squared. Then I have what? Negative 18y plus 4y, negative 14y. Then the 4 times negative 6 is negative 24. In parentheses, 5 to the first, y to the second. I don't know if I need that 5 to the first. Probably don't. Now, I'm going to use the distributive property. I don't expect to see these arrows on your work. But they are understood, okay? So, it looks like wallpaper. 15, y to the what? The fourth. Do we agree?
Yes.
Ephraim. Okay, then minus 5 times 14 is a big 7-0. Y to the what? Third, and that's where it helps to have this 1, Isaac, with the exponent on the y that we talked about yesterday. Then minus 120 y to the second. Does that answer?
Yes.
Okay, James, you had a question. Right. Yeah, okay. Open parentheses. 6a minus 9. Oh, boy. This is the worst of the worst. Right? So, what we do, you have a choice here, and I don't know which you prefer. One is to take the 6a minus 9 and multiply it by each of these, or take 6a and go across and then take negative 9 across. You wanted to do that? So I'm going to take this part first. Get that. Then I'll take this part and do this and add them all together. Now, that wouldn't make a bad tie. I like that. Okay? So, you have 12a to the third, and that's where Isaac, the 1 again, just got to keep you watching, so, and a 1 there, in case you didn't see them. 12a to the third, then plus 10a to the second, plus 54a is the first product, where I took the 6a times all that. Okay? Took 6a times 2a squared. That's 12a cubed. How about a 30? A squared. Then the 54a. Now we're in business. I have no idea where that 10 came from. Okay, now the negative 9. I'm going to put that down here at negative 18a to the second. So I'll just fit it under here rather than stringing it out. Then a negative 45a and a negative 81. So this is a little bit like stacking them, but I think it's an effective way since you chose to approach it that way. So 12a to the third, then I guess I have a 12a to the second. I have a plus 9a and a minus 81.
Yes.
Any discussion on that or where it went? Okay. It was the hardest problem in the set. Now, you had an alternative, and that was to take 6a minus 9 and multiply it times here. Okay, I would have this, which I'd have times 2a to the second. Okay. Now, just a comment, Natalie. With that microphone right there, if we have that up to pick the other sounds, then I pick you up too. So it helps if you sort of don't. 6a minus 9 times 5a, and then plus 6a minus 9 times 9. I can't go anywhere in B. I'll just step here and you can see that much. Then what do? Reverse each of these, because I think that helps to see 2a squared times 6a minus 9. Then I rewrite this one as plus 5a times 6a minus 9, then plus the 9 times 6a minus 9. Then the distributive property again, which is going to be 12a to the second minus 18, how about a to the third, add the exponents, 18a squared plus 30a to the second minus 45a, I'll get out of your way in a minute, 54a minus 81, and I'm just walking off camera.
That's more right.
It's more writing, but it's technically the way it's supposed to be done. Now, what do I still have to combine? I have the 12a cubed here, and that matched the 12a cubed you saw up here. Then I'm going to have to take the 30 and the negative 18 to get the 12a squared here. Then I've got to take the negative 45 and the 54 to get the 9a up here, and then finally the negative 81. So this whole thing comes into here when I add like terms. Enough. Okay? Now, coming back center. It is the worst problem of the set. Do I expect you on a test to be able to whip that one out? No. Do I like pushing you on the homework so you can try to do that problem? Yes. If you struggled with it, okay. The problem above it, before that, which was coming back here, Ernie, up to here, where you had this binomial times a binomial times a monomial, that, I think, is a fair test question. Okay? So, if you stressed on the bottom one that we just did, I understand why you would, and don't get upset by it. Okay, a question on this one still? Before you have a question, Bolmaro had a question. It's on this problem?
Yeah, which step do you recommend? I like going to the bottom.
You like going through this? That would be fine right now. I think it's the best thing to learn. And I'm not going to give you on a test a question like that because it takes a lot of steps, it takes a lot of work, and it's very easy to blow one. When I did the a squared here, and because I didn't see the 1 there, I was working too fast and nearly had the error. So you sort of, I like carrying this through, ideally. In practice, what James was talking about is precisely what I do. I'd take the first one, multiply through, take the second, multiply through, stack them, and get my answer. You choose. Doesn't matter there. Either way is acceptable. Soshi, you got a question? Where on the column? This one? Up here, this 14 here? Ah, the outers and the inners. A frowning face. That's negative 18, correct? 3y times negative 6 is negative 18y. And the inners is a positive 4y. So here I have a negative 18y. Here I have a 4y. And then I add those two together to get negative 14. Okay? Other questions there? Dion?
So that close parentheses outside of the 4 and the open parentheses next to the y, it recognizes that's where you
Here?
Where you would recognize the multiplication.
Yes, because those two parentheses are next to each other. We don't put a dot between them. Yeah, good point, because we've been doing a dot, and suddenly the dots are gone. There's another hand up. I don't. Sandra, we're back to here.
Yes.
Okay?
Which one would you say is more effective without making the small, errors? Because
Most effective without the errors, this.
that one?
The only place here I think you have to be careful is that minus 9. You remember you are taking the negative through. So you might want to write that as 6a plus a negative 9. I'd be inclined, as I say, to do this and have minimal errors.
Okay.
Down here where I write these and then reverse the product, anytime you write down a line 2 times, you have the potential of just some little careless mistake.
Right.
So if you can minimize the number of lines you're carrying through, the better. This is more cost-effective time and energy-wise. This is conceptually important, but that's really a 70 problem. And we throw a 70 problem that would be much more in 70 than 20 every once in a while at the end of a set to push you just a little bit further. Not off the cliff, but just a little bit further.
So in 70, are they going to require that way?
If I were doing a 70 class, you would hear my same presentation. I would make the same arguments
So
either way. Except I'd have it on the test and expect you to be able to do it. That would be the difference, okay?
Do it this way?
No, just this kind of problem.
Okay.
Your choice on doing it. You certainly aren't going to do this one in your head without writing something in between.
Right.
You can't do something like FOIL and just look at the problem and say, there's the answer. Done. Anybody else? Or does that take care of the questions? Very impressive. Do we always carry waffles around? Do you know how many squares are in the waffle minus the ones you've eaten? I just thought I'd ask. I see squares and I see problems in mathematics. You can find the area of that resulting figure now. Okay, just thought I'd say that in passing. We have a new section today that is a welcome, old-time visitor. Prime factoring. Deja vu time. 3-5. Nancy, was that protest or just... Let's just look at some of the things that are done here in 3-5. And first, something I'm going to oppose. Yes. It's not that I'm anti-ecology or anti-trees, but I don't want factor trees. I want the division like we've been doing it. Okay, so if I'm going to look at 42, I would like to see you factored into a product of primes in the usual way. The factor tree is a nice shortcut, but since we did it the other way, I just assume we do our factoring in that way. So that's the one difference. I'm on page 202, which is a palindromic number. Okay, 202, palindromic number. Now, right below that, there is a new phrase, the only thing that's new in this entire section, the GCF, greatest common factor. Okay? So let's come off there for a moment, Ernie, and I'm going to go to the board behind me and do a problem that's not really in this as much as it is in Math 10. But I'm going to show you an idea that I hope will pull this all together. This is without pre-planning. This just hit my head. Okay? So, as so many things that I do in my presentations. So let's try it. You are familiar with this phrase. True? And you know what I mean by that. So if I give you a problem like 48 over 56, we could cancel, but what I expect you to do is to write both 48 and 56 as a product of primes. So 48, okay, is going to be 16 times 3, and 48, as the 16 times 3 could be written as 2 to the 4th, so that's 2 times 2 times 2 times 2 times 3, over, then we have 8 times 7, so you have 2 times 2 times 2 times 7. So far okay? I didn't do the division, but are you with me? Because 2 to the 3rd is 8, 2 to the 4th is going to be 16. Now, if you'll look at what you would typically be canceling, you'd cancel all those out, correct? And you'd be left with 6 over 7, right? Now, if I just sit there and cancel, we say 8 goes into here 6, and 8 goes into there 7. That would be canceling, getting the same answer. These three factors are common to both numbers. Just like we had common multiples. So these three factors are common factors. And in fact, they are what? The greatest common factors that you can have there. So if you look at it in terms of what we're talking about, the greatest common factor is just 8. Look at the monitor if I'm in your way. And there's one right behind you if you're not able to see as well. But I'm going to change the problem. The 48 is 2 to the what? 4th, 3 to the 1st, correct? And this was 2 to the 3rd, 7 to the 1st. What primes are common to both numbers? Only the 2, correct? And then instead of looking at the highest exponent, I'm going to look at what? The lowest exponent. That's the trick. Okay? Now, we're going to complicate it by putting letters together. Okay, when we get to factoring very shortly. So if I look, okay, what I'm going to do, Ernie, you're on what, 2 now? Will you bring 1 back over to that problem, please? And I'll be going there next. So whenever nod when you are there, okay? Now look at this one. What's common in every term here? There's a y in each of them, correct? What was the lowest exponent? The 2. So y squared's common, correct? Now I could technically write 15 as 3 times 5. So I'd have 3 to the first, 5 to the first. But I also notice that there's a 5 in this, and a 5 in this. There's no 3 here, so it couldn't be common to all of them. So the 5's common to all of them, so there is my GCF for that trinomial. Same idea. Look for, in this case, the variable that's in all terms. Then look for the lowest exponent. And I could have factored all of these into prime factors, but what I did was selectively say, well, this is only 3 times 5. If 5 is a common factor, it has to be a divisor of every coefficient. Divisor of every coefficient. It is. Ends in 5, ends in 0, ends in 0. Is 3 a common factor in every term? No. 7 and 0 is 7. 3 won't go into 7. Hence, my GCF. Then what we do is say, take this greatest common factor out and write this. And that's what we do tomorrow, called factoring. Robert. If I had a 121 instead of the 120, good question, then y squared would be my GCF. Because 5 and 3 would not have been a factor here. It's a good question. Okay? Now that pretty much covers today's presentation. And I was very tempted to go right into the next section. But I have a hunch that I'm over-optimistic or overly optimistic in my thought that this is a slam dunk. So I've got to find out just how good we are at this. So I'm going to come back. We'll just, I know you had to resume, but notice that resume. Ernie, you didn't even smile at that. That was a pretty good pun. Huh. Okay. Let's go back to the beginning of this section. All the way back to page 193, and the title of this in section 3.5 is, as we go to the document cam, prime numbers and a GCF. And then note, the objective, to determine if a number is prime, composite, or neither. Okay, now that's an interesting idea. Technically, 1 is what? Not prime. We don't call 1 a prime, and we don't call it a composite. So it's neither. But the rest of the numbers, we classify in one of 2 categories. So we say 37 is prime. 33 isn't, because I can write that composite as 3 times 11. And the important statement we had in mathematics, we spent a lot of our time getting frustrated doing it, writing every composite as a product of primes. And it can only be done in one way, and sometimes it does get challenging. The definition for a composite could be any natural number that's not prime, other than 1. Okay? So natural numbers. Think like counting numbers, a natural number like a counting number. So a natural number that has factors other than 1 in itself. If a number can only be factored in 1 times itself, we call it prime. So you could have simply said A composite is not prime. Out is not in. Hate is not love. Okay. Stop is not go. Three little questions here. You could answer these now. You better be able to. Let's go to the three questions. This is based on 10. That's not reading big enough. I'll just bring it down. There we go. Every prime number is an odd number. True or false?
False.
False. Very good for three of you. Why is it false? 2 is prime and 2 is even. Well stated.
3 is odd.
Okay, well, let's go to the part 2 now. Is every odd number a prime number? No. Give me a counterpoint. Counter example. 27, odd, not prime. 9, odd, not prime. Okay, ad nauseum. We can go forever. Okay, last one. Is every even number a composite number?
True.
You got trapped. Sandra's 2. Okay, now every other even number other than 2 is composite because it can always be divided by 2. But 2 is that one little wrinkle. Every other prime is odd. 2 is all by its lonesome. Question? Natalie? 15 is a composite. Okay, but this just says, is every even number? 15 is odd. Okay? Gotcha. Now, we can list the primes, and what did we find out about the primes? I told you that they never end. They go forever. Primes forever. That's a good phrase if you have Buzz Lightyear at your house. Okay, to infinity and beyond, primes forever. Yes?
Can a fraction be a prime number?
A fraction would not be considered a prime because a prime is a natural number and a fraction is not what we think of as a counting number or a whole number. Okay? So it would by definition not be allowed to be prime. Any questions on the primes there? And you're supposed to know the list up to about 19 without any problem. You've done that enough, and if you can't do that right now, you might want to review again. You know, the 2, 3, 5, 7, 11, 13, 17, 19, go that far without even thinking. Good. This process of determining whether a number is prime or composite, I just want to review this. This is on page 195. 157, you want to determine if it is prime or composite. So what did we do with a problem like that when we were trying to show something of this nature, whether it's prime or composite? What did I ask you to do first? And I didn't give you a nice number like this. What do I have to do first? List my primes. Yes, the 2. We come over to the side. 2, 3, 5, 7, 11, 13, 17, 19. Now, my question was about what? 157. What's the last prime I need to worry about? Go higher. Go higher. Why? Not square root. You're thinking the right thing, but you have a different phrase. The square of 13 is what? 169. Well stated. Who said that one? Anybody else know that besides Jessica? Good. 2, 3 of you? All of you should. Robert, yes, it was on the test. Thank you, Robert. That was excellent. Did you get it right in the test? Very good. Okay. So do I have to worry about 13? No, but I do have to worry about 11. So I do have to go past the 7. Now, what do I then try? Well, I try everything in this list and ask, will any of those numbers go into 157? If they don't, none of these primes divide into 157, it is prime. And I don't have to go any further. That was the key in Math 10. Divisibility rule for 2. Last digit has to be even. Done with that. Divisibility rule for 3. Add the digits. And what must be true when I get that sum? Okay, divided by 3. We get 13, can't be done, done with 3. Divisibility rule for 5. Bless you. 5 or a 0. It's neither. We're done with the 5s. This is fun. Okay, only 2 left. 7. If I divide by 7, short division, remember that? And 7 won't go into 17 evenly. Done with that. The next one is 11 into 157. Whistles, fireworks, we're nearly done. Celebration time. It goes 1 with the 4 left over. Didn't work. I'm done. 157 is prime. Now, if the number's big, like 2003, not so easy. Particularly if nothing seems to divide. And I gave 2003 to my Math 10 class at 11 o'clock for them to do for a homework problem. But you had similar problems, so we won't do that. Okay, let's come back to the document cam for a moment, Ernie. So we now know what? 157 is a prime number. Is there any way that we could determine what the primes are? There is a correct answer to that. Is there anything I can use to get primes? Guaranteed. Think of spaghetti. A sieve. A sieve of whom? Eratosthenes. You look at me with that look. Okay, Ernie, back to the sideboard briefly so I can give him the sieve of Eratosthenes. Before I do that, let's see if I can do something here. Just a minute. Let's try this. Oh, yes, came right up. Excellent. Okay, let's cut to the document cam. There it is. Eratosthenes. Isn't Google wonderful? Eratosthenes. 276 BC to 194 BC from Greece. And he was a mathematician for his work on prime numbers. What? 285 to 194. Well, they disagree by 9 years. Okay? But he was older than what you said. Okay, now, what I'm going to do here, this will maybe save me some work, just maybe. What I'm going to do is come up a little bit higher. There we go. I'm going to type in sieve. Of. And let's see what we get. If Stephen Colbert can do this on TV, I can too. You don't watch him, huh? Okay, sieve of Eratosthenes. There we go. The sieve. And it's an ancient algorithm used for finding primes. So let's see if it gives us anything we can see here to save me writing. Oh, it does. You gotta love this. There we go. It's showing you what happens. It's watch just as it goes through. That is neat. Do you know what's happening? Just keep watching the colors. Went blue. Next one, watch for what's happening to the 7. It went yellow. This is worth the price of the show today. Then it went to 11. Next one will be 13. Watch what happens to 13. It's in purple. Then it'll go to the 17. Okay, let's just let that go for a moment. So you understand what's happening there. It starts again. Now, circle the 2, and then you cross out. Go 1, 2, cross out. 1, 2, cross out. 1, 2, cross out. 3, then count 1, 2, 3, cross out. 1, 2, 3, cross out. 1, 2, 3, cross out. I can't do it as fast as that. While you're watching, I'll write what he did. And in a moment, we'll have Ernie come to the sideboard, because this is the only technique that I know of that will guarantee you, when you get done, the primes. It's just very tedious. The computer does it very fast. Okay, come to the board, Ernie. And I'm not writing these numbers very good. I circle the 2. And all that you saw happening on the screen was saying, now count. 1, 2, cross out. 1, 2, cross out. 1, 2, cross out. All that was done on the screen was a green box. Let's go back to the document cam. See, when it's doing the 2, maybe it won't. There we go. See how the 2 is going to the green each time? It just does it a whole lot faster than I did. Then we do what? I guess the green was the 2, 3, and the red was 2. So I'm going to go to the 3, and then I do what as I come to the board? 1, 2, 3, cross out. 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 1, 3, cross out. Then I do what? Go to the 5 and do what? Go 5, cross out. 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 What is left? Well, I didn't cross out my 2's all the way, which I should have. My apologies for that. Because if I'd crossed out the 2's, all those would be gone. And I'm left with what? 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. And those are the primes under 30. That's the sieve. Yes?
If you were to make that chart up to 1,000,
then you'd have the primes under 1,000. Now, the last number you have to circle and cross out is the prime just smaller than the square root of 1,000. So 30 times 30 is 900. 33, 34, and 35 are all composites. 35 squared is 1225, so the last prime you'd have to check is 31. So you circle 31, count 31, cross out, and you'd be left with the primes. So it's a neat technique. Let's go back to the document cam and watch it one more time. Well, Eratosthenes is not around for me to ask. Michael's asking, how would he figure that out? I have no idea what he was thinking or what he was drinking, but in terms of the process, he got very creative. And just watch this one more. No, let's go back to it. It's fun to watch. I mean, where else can you see a show like this? There we go. I mean, it's just like... Now, what I can't show you is this is a list up through 120 is what's going, and I can't get down to 120. That's why there's a pause. But notice, each time over here on the right side, they're showing you the primes as they carry them through, and they're going up. Otherwise, they're generating the primes now, and these are the primes under 120 when you're done, which is very nice. And the last one, under 100, was a 97. And as we carry that down, the last one listed here is 113. Okay, coming off there. Now, yes, Michael.
I remember you saying that they're constantly working on defining
Yes.
the prime number.
We're hunting for primes all the time for national security to do encryption.
Is that the system that they use to find it?
No, the process of division, by checking the divisors, there's some nice, clever shortcuts you can take that make the process faster in a computer for very, very large numbers. So as fast as supercomputers go, they can do shortcuts in divisions. They can take an accumulation of information about divisors. We stopped at 5, right? But there are some nice rules that you can go beyond there that make it a little bit easier. So there are techniques, but none of them, there's no formula, no general rule other than the sieve that I'm aware of that will generate primes. Now, if you say, I have the primes, all the primes under 1 billion, and I want to go to 1 trillion. Well, you could do it with the sieve, but then there are some constraints about how many digits you ultimately can store in a computer program. So if you get up to 1 trillion digits, and that exceeds the capacity of what you can do in your computer, then it's not a very effective tool. Primes. Determining whether they're composite or prime, you just do what I did in the board there relative to that division problem we had before we went to the sieve. Okay, now let's see what else we can do here. I'll just let the computer keep doing that. As I cut over, I didn't quite state this direction the same way it's in this text. Find the prime factorization of a given number. What was the phrase I used? A product of primes. So a product written with prime factors. That's what it means. So if I gave you 48 and I said write as a product of primes, that's called prime factorization. So language here is adjusted slightly as we go further. The procedure that's given here in page 197, where you find a factor tree, I have mixed feelings about. And let me explain why. We're talking about branches, hence trees. But if you're going to go ahead in mathematics and you come to a problem in statistics and probability, we sometimes show outcomes of experiments doing something like this. I just need to clean this up. Robert, could you hand that eraser to me over there, please? I know you have to get up, and I apologize for that. You can go back and rest again. Now, if I want to list the outcomes for rolling a single die, didn't need that much. I'll come back here. I got carried away. So a 1, 2, 3, 4, 5, and 6. And we talk about a tree diagram. So a factor tree is a concept that's important. Now, if I follow that up with tossing a coin, roll a die, toss a coin, then I can list the outcomes of this experiment using this tree. And this is something we do in statistics, and oftentimes I will make this statement. Maybe you've done a factor tree that you would have seen in another course. So I'm being a little bit less than honest when I say you don't need to do a factor tree. But if you can understand what I'm doing there, this is your toss of the die. This is the toss of a coin. So you have a 1 and a tail, a 1 and a head, 2 and a tail, 2 and a head, and so on. So I have 12 outcomes. And we list these as pairs. And so on down the list. It's not that I want to have you understanding probability, but the tree idea comes back. Let's go back to the document count. So the factor tree I'm not holding you accountable to. If you like it, it's not a bad idea, but I'd like to see the divisions. So we don't have to learn anything new there. That's straightforward. We come to the greatest common factor. We've talked about that. The rule here, first the definition, the greatest common factor, and it's the greatest divisor. I think that's the statement he makes somewhere here. Let me come down. Note the greatest common factor is sometimes called the greatest common divisor. And notice in terms of numbers, it's the greatest number that divides all of the given numbers with no remainder. That's on page 199. Well, as I come to the front board now, Ernie, with camera 2 behind me, and we're okay, but just looking at this, remember this was a greatest common factor, and it involved a what? A variable. So that definition is a little bit restrictive, just numbers, because we're going to talk about the GCF. Coming back, to find the greatest common factor, you list the factors, otherwise write it as a product of primes. Then search the list for the greatest factor let's come back over to, okay, bring camera 2 back around here. The heck with 1. Come back to here. If you understand this example here, I think that's as important as anything. You're hunting for any, okay, waiting before I go to that. You're looking at the primes, and we did it in terms of exponents. And so the key was, what's the common prime and the lowest exponent? If you can picture that as a model, then you understand the greatest common factor. Now I'm going to go back to center M1. The procedure using greatest common factor with prime numbers is on 201. So if you just want to reference that, it's done exactly as I was talking about it. Here is an example sliding down the GCF of 3024 and 2520. Notice the common 2, the common 3, and the common 7. I would have preferred it had there been an exponent of 1 on the 7s. But you can see immediately that you're going to have a 2 to the 3rd, a 3 to the 2nd, 7 to the 1st. And that's exactly what we see for the GCF. That's the problem I think is critical that you understand. And I don't anticipate any difficulty there for you as you do the problems. This is where it extends to what I just did in the board at the very end. I'm on example 7, page 202. Do you see that the greatest common factor is going to have to involve x cubed? And then you look at the 18 and the 12, and I hope you realize the 6 is the biggest divisor that will go into both of them. So your answer is 6x cubed. You're done. We okay there? You could write 6 to the first, but not typically. The only point, as I was explaining to Isaac in writing 4 to the first, was to remember that you have an exponent on there, and in that problem he asked about it was a critical issue. That's it for the section. So being done with that, the problems, and let's see, I gave you the list of problems, right? Can you just tell me what the last problem number is on 3.5? I put those on the website for everybody just between classes. For 3.5, what's your last number there? 67? Okay, if I look at problem 67, and this is unfortunate because the GCF there is just a 10. I mean, there's nothing exciting about that. And seriously, I don't have anything after 67 on 3.5? Okay, so we go down to 77, and yours is going to look different on the computer for those of you doing it there. But looking at 77, your common variable is what? N, and the lowest exponent is 2, and what's the largest number that will go into 18, 24, and 30? A 6. Now you could write it in prime factoring, but you don't have an obligation to do that if you can just eyeball it and see it. Pardon? So it would have been, yes, 6n to the 2nd would have been your answer. Any questions there? Okay, just stretching. Okay. I don't think this set is terribly demanding. I'd like to take a moment to see the next section because it is going to be more demanding. 3.6. And technically, we are not having to do that today. But let's look at it as we go to the document can. Introduction to factoring. Now, there are a couple things that are going to be involved here, but what I want to do, Ernie, is come back to that problem where I factored out the 5y behind me, this one right here. So I want to come back to this for a moment. When you see a problem like this and you're asked to factor it, you hunt for the GCF. If you can see this GCF, then in essence what you have to do is take the, I was going to say polynomial, I'll just say trinomial. The trinomial here and divide it by this. Now, I want to leave that on the board, Ernie. Are you in 1 or 2? Okay, we come back to 1 on this one, so free up number 2 so I can go to the side. And then what I want to do, and this is a risk of my part, I'm taking a leap of faith here. But first I want to ask you this question before, okay, coming to the side. A plus B over C. I need to have you understand that that's A over C plus B over C. Does that seem logical to you? We said 2 plus 3 over, let's say, 11 is going to be 2 over 11 plus 3 over 11. Okay? Not a problem there. Now, let's go back to camera 1. I'm going to write what I have up there, and I think I got just enough time to carry this off. I observed, and I have a 5 first y to the second. Okay. I said this was my trinomial, and I observed this as a GCF. Okay. So I'd like to write this in factored form. Now, I'm doing this to explain this is not what I do in practice. Same argument. And notice, Isaac, the 5 to the first. It makes sense based on what we just said. Okay? Now, what is this going to give you? A 3 what? Now, you're a little bit hesitant there. This is y times y times y times y divided by y times y, which is going to give you y to the second. I want to come back to that. What's this one going to give you? 5 into 70? 5 into 70? 14. Y to the third over y to the second. Y to the first for Isaac. What's 5 into 120? Look where it came from. 24. So I divide by this and then say that this, which was the quotient, multiplied by the divisor, gives you the dividend. That is, the factoring is 5y to the second, open parentheses, times 3y to the second minus 14y minus 24, and I have now written this particular polynomial as a product of a monomial and a trinomial called factoring. Now, there was a very important step here that we said we have y to the fourth over y to the second. And we said that was equal to y to the second, correct? We have y to the third over y to the second. And we said that was y to the first. Y or y? The y? Okay, if I have a to the m over a to the n, it is a to the m minus n. New rule. Don't groan. You'll remember that we said if we had a to the m times a to the n, we added the exponents. When we divide, we subtract the exponents. Zoom in on that, please, Ernie, and I'll walk off camera. That is given to you on page 207. It's a little bit like the intermediate step. We've done this before. As we go back to the document cam on page 207, and nobody does n to the a and n to the b. I'm sorry. But anyway, if you did that, you have n to the a over n to the b is n to the a minus b. And I have a to the m over a to the n. That I don't like. Anyway, There it is. And n cannot be 0 in this particular case. The problems are set up for 3-6 already. There's about 20-some of them that you're going to be doing. So your key, of course, is to work on 3-5 tonight, get that done. But we're going into 3-6. And if you were to look at the problems that are in the examples, I think you're going to find that this is a little more challenging than the other set. So with that, I want to go to the slide.